Hello, dear students. Today we will discuss about the paper refrigeration and air conditioning, and the topic is air refrigeration cycle. And my lecture's outline is the definition of refrigeration, unit of refrigeration, and the definition of COP of pump, refrigerator, and engine. The definition of refrigeration, it is defined as the process of removing heat from the substance under controlled conditions. For example, this is one of the refrigerator. Inside of the refrigerator, here we are removing heat, and for the process different component used like a compressor, condenser, expansion device, and evaporator coils. When we are receiving heat from the space, inside space of the refrigerator, the process is used, and that process is known as refrigeration. The process we are adopting for removing of heat from the substance, and that process is known as refrigeration. And next is the unit of refrigeration. Obvious, the unit of refrigeration is the ton of refrigeration. It is symbolically it is told as TR. T for ton and R is refrigeration, ton of refrigeration. So ton of refrigeration is defined as the amount of refrigerating effect produced, or the amount of heat required for uniform melting of 1 ton of ice from and at 0 degree in 24 hours. Suppose we have to take a sample, 1 ton ice, means 1000 kg ice at 0 degree temperature. At that temperature, we need to supply heat for uniform melting. So heat addition continue. What happens? The ice at 0 degree, it will convert water at 0 degree. Only phase change occurs. There is no change of temperature. And in the calculation part, suppose the latent heat of ice 335 kilojoule per kg. For 1 kg ice, if we want to change the phase, then it needs 335 kilojoule heat addition. So for 1 ton, 1000 kg, it is 1000 into 335 kilojoule. So it is 335,000 kilojoule heat addition required in 24 hours. That means in a single day. So next calculation part, if we want to know the amount of heat addition required in 1 hour, then we have to do 1000 into 335 divided by 24, and that much of a kilojoule heat in 1 hour required in 1 hour. And again, if we want to know the amount of heat addition required in 1 minute, then again you have to divide 60. So it is 1 ton of refrigeration is 1 TR equal to 1000 into 335 whole divided by 24 into 60. and the value is 232.6 kilojoule per minute. It is calculated value 232.6 kilojoule per minute. But actual practice, in actual practice, it is taken as 210 kilojoule per minute. For international standard, the 1 ton of refrigeration is 210 kilojoule per minute. If we want to know, suppose the value of 1 ton of refrigeration in kilojoule per second, then again we have to divide 60, and 210 divided by 60, then it is 3.5 kilojoule per second. So 1 ton of refrigeration unit is very important. First of all, any components if we use, we have to know the unit of the component or device, and 1 ton of refrigeration is 3.5 kilojoule per second or 3.5 kilowatt. Suppose in our home appliances, so many refrigerator, air conditioner use, suppose 1 ton AC, that means the heat extraction capacity is 3.5 kilojoule per second or 210 kilojoule per minute. If it is 2 ton, then obvious 3.5 into 2, 7 kilojoule per second, or 210 into 2, it is 420 kilojoule per minute. So next part is the definition of heat, COP of heat engine, or the efficiency of engine. In engine, what happens? Normally, we use to supply heat to do some useful work. This is suppose the figure of a steam engine. Here, heat is supplied, tremendous amount of heat is supplied to generate steam, and the container, which is water, is present, and due to the supply of heat, the water get converted into steam, and the steam, it increase the pressure, and high pressure steam is allowed to enter inside the piston and cylinder. When high pressure steam enters inside the cylinder, it will push the piston forward. The direction of movement of the piston given here, it will move forward, so that the end of the piston, the mechanical lever or linkage given, so that the wheel will rotate in clockwise direction. Suppose in this figure, if wheel is rotating, then obviously we will do some work. And most of the thermal power plant, what happens in this process? Suppose generating steam, and steam is given, supply is given, and at the center of the wheel there is a shaft. If we couple a generator, then definitely we will produce power also, electricity. The heat supply is given through the different fuel. For example, petrol and diesel, the calorific value of petrol and diesel almost 45,000 kilojoule per kg. If we use petrol, 1 kg of petrol, then after complete combustion, it will produce 45,000 kilojoule heat. So that heat is used to run the engine, automobile engines also. In automobile engine, what happens? Inside the engine, there is a combustion of fuel, and after combustion, it expands and used to run the engine, and by the engine, the piston movement of the engine, power comes to the wheel. This is the schematic diagram, line diagram of the heat engine. Suppose the high temperature reservoir and it will supply to the heat engine, and some work done in the engine and the low temperature reservoir. After use of steam, it will exhaust to the next cycle or exhaust to the atmosphere. In the ice engine also, it is also exhausted to the atmosphere through the silencer. And the Q2 is the heat supplied in the engine, and Q1 is the heat rejected from the engine. Then the net work done by the engine equal to the difference of heat supply and heat rejected. So work done by the engine W equal to Q2 minus Q1, where Q2 is the heat supplied and Q1 is the heat rejected. And that difference came due to some useful work. Heat is converted into the mechanical work. The performance of heat engine, it is expressed in the efficiency of the engine. Normally, the efficiency always it is ratio of the output by the input given to the system or the machines. And here in engine, the output is work done and input is heat supply. So efficiency of engine or COP of engine, that equal to work done by heat supply, and work done equal to Q2 minus Q1 divided by heat supply Q2. That is work done by the engine W divided by Q2. Next is the coefficient of performance of the refrigerator. If we think about the refrigerator, the coefficient of performance, it is the ratio of heat extraction capacity to the work done on refrigerant. What amount of heat extracting in the refrigerator to the what amount of work input given to the refrigerant. In diagram, this is the surrounding temperature, suppose T1, and this one is the refrigerator, and this is the body temperature T2. Always T1 is greater than T2. T2 is the temperature inside the refrigerator, and T2 is less than T1. Still, heat is flowing from lower temperature to higher temperature by the use of refrigerator. And how it is possible? Due to some work input given through the refrigerator. Unless otherwise, if you are not giving work to the refrigerator, so it is not possible the flow of heat from lower temperature region to higher temperature region. In between the two temperature regions, suppose T2 and T1, where T1 is the greater than T2, still heat is flowing from the inside space of the refrigerator to the surrounding atmosphere by the application of refrigerator. In the refrigerator, what happens? Some amount of work input given to the refrigerant. And the COP of refrigerator, the theoretical COP of the refrigerator, that is refrigerating effect divided by work done. And the COP of refrigerator, it is refrigerating effect is the Q1 and divided by work done of the refrigerator WR, and Q1 and work done is the difference between temperature Q2 minus Q1. Next one is the heat pump. The COP of heat pump. Heat pump simply it deliver heat from cold body to a hot body. From a cold temperature region to a hot temperature region. If we think about the cycle of operation, it is nothing difference between the cycle operation between a refrigerator and heat pump. Only the difference is what temperature it is operating. In a refrigerator, obvious the temperature range is less, and in heat pump it is more temperature difference. So in heat pump, this is the schematic diagram. Suppose outside air it is a low temperature or cold body, and this one is the useful heating we want to require. By the application of heat pump, and there is some compressor and electricity supply given to the compressor, and the heat pump which receive heat from the lower temperature region, the outside air, and deliver to the particular space which is required to increase the heat source. And in case of coefficient of performance of the pump, or it is sometimes told as the energy performance ratio EPR, it is the ratio of heat delivered to the work done, and Q2 is the heat delivered, and WP is the work done by the pump, and it is Q2 divided by work done is the Q2 minus Q1. So this is the ratio is called coefficient of performance or energy performance ratio. So thank you.